Welcome to the 8th part of this series of video dedicated to electronic simulation with thermistors and RTDs. In this episode, we will be reviewing several heat detector circuits, all based on NTC thermistor SPICE models. Here is a siren buzzer circuit based on a cascade of two 555 timers. Some words about the circuit behavior before we do the simulation. When the temperature is normal, Q1 is conducting and the SW node voltage is kept low. As temperature increases, the NTC resistance will decrease, the voltage at the NTC node decreases, and at a point Q1 is blocked. The 555 timer U1 is reset. Vout gives a pulse signal which will reset the second timer to produce a new pulse at another frequency. That's the siren noise. In fact, LTspice 17 allows to save voltage as some files so we can hear it now during the video. So let's go for a simulation. We set the fire alarm circuit on with the start switch. We apply the temperature step and watch your ears now. It's over. Hopefully it was a false alarm. You see and hear that the noise stops when the NTC temperature goes back to a normal value. Not only the simulation results corroborate the intuitive ideas about the circuit behavior, but they allow to quantify all design parameters, especially if one introduces tolerances for the thermistor and resistors characteristics. If we want the noise of the fire detector to stop only when the power supply is switched off, we can add this SCR to the circuit. So in this case, even if the thermistor goes back to normal temperature, the siren noise will go on until we switch off the power supply. So let's go for a second noisy experience. The detector is switched on. The temperature increases now. So we see effectively that the alarm stops only when we switch off on the power supply, long after the thermistor is back to ambient. This brings more security to the heat detection for the case where the thermistor would go into open circuit after alarm has started. A manual switch off of the siren is in this case necessary. So enough for today of this annoying siren buzzer noise. So we can go back to a simple detector with one 555 timer. Yet with another new feature. This circuit is a rate of rise detector. It will work with the speed of increase of temperature rather than with a fixed level. It contains two NTC thermistors. One exposed which reacts quickly and another protected with slower reaction. If the temperature variation is really slow, like for a natural variation of ambient, even rising up to 50 degrees C, the switch will not happen, as the voltage VB will remain constant. At the contrary, if the variation is faster than a predefined threshold, the exposed thermistor value will decrease before the other, VB will reach the required low level, and the detector will switch on. Let's confirm all these provisions with a simulation where we apply temperature gradients which are going to be slower and slower. We will see then when the detector will not switch anymore. Let's look at the results of the first simulation. We see how the two NTCs reacted differently in speed to the gradient and that the detector switched when temperature has reached 50 degrees C after 110 seconds. We see here that the switch happening at 12 degrees C per minute does not operate at 6 degrees C per minute, even if the final temperature is the same around 50 degrees C. When we plot all the results in function of the gradient intensity, we conclude that the detector does not switch with a gradient under 6 degrees C per minute and switches 100% for a gradient above 7.5 degrees C per minute, which is in fact the goal of this rate of rise detector. Well, this ends up the part 8. I hope that you enjoyed the video. Thanks for watching.